Next question is, in a certain SSB generator of phase shift type, the phase shift of the modulating signal is deviated from 2 degree from the ideal value of 90 degree. Find the ratio of undesired sideband amplitude to the desired sideband amplitude. So this is a problem of SSB generator and it is a phase shift type. We know that in phase shift SSB generator, we have two balance modulator. Balance modulator 1 having input signals of modulating signal cos omega mt and carrier signal of cos omega ct. Here for our convenience, we take the amplitude equals to 1. And for balance modulator 2, we take input signals after passing through 90 degree phase shift. So the input of balance modulator 2 is cos omega mt plus 90 degree correspond to the modulating signal, and cos omega ct plus 90 degree, that is equals to sin omega ct corresponding to carrier signal. So for balance modulator 2, the modulating signal is sin omega mt. Here the output of balance modulator 1 is V1 and output of balance modulator 2 is V2. These output signals are added using summer. And in order to get single sideband, we take positive sign with respect to V2 for LSB retained and negative sign with respect to V2 for USB retained. And we get output correspond to amplitude modulation single sideband suppressed carrier. Now here we consider USB retained, means we suppress the lower sideband, and the output is V0 equals to V1 minus V2. In place of V1 we can write cos omega ct into cos omega mt, and in place of V2 we can write sin omega mt into sin omega ct. That is the output of balance modulator 1 and balance modulator 2. Now we have a formula of 2 cos A cos B. For this we first multiply and divide by 2. So the first term is 1 upon 2 within bracket cos omega c plus omega m into t plus cos omega c minus omega m into t, and the second term is 2 sin A sin B. For this we multiply and divide by 2 and we get 1 upon 2 within bracket cos omega c minus omega m into t minus cos omega c plus omega m into t. Now we open the bracket. So here we cancel a term correspond to frequency omega c minus omega m, and we get only upper sideband, that is V0 equals to cos omega c plus omega m into t. Here the lower sideband is cancelled out. Now we consider our problem, and according to our problem, in this the phase shift of the modulating signal mt deviate by 2 degree from the ideal value of 90 degree, and we have to determine the ratio of undesired sideband amplitude to the desired sideband amplitude. So here the output of balance modulator 1 is V1 and it is equals to cos omega ct into cos omega mt, and the output of balance modulator 2 is V2 equals to sin omega ct into sin omega mt plus alpha. Here alpha is 2 degree, that is deviate from the ideal one, and in terms of radian it is 2 pi upon 180. And here the deviation is 2 degree, which is very small with respect to 90 degree. So this value of alpha can be approximated, and the output V0 equals to V1 minus V2. In place of V1, we can write cos omega Ct into cos omega Mt, and in place of V2, we can write sin omega Ct into sin omega Mt plus alpha. Now, sin omega Mt plus alpha can be written as sin omega Mt into cos alpha plus cos omega Mt into sin alpha. And since the deviation, that is 2 degree, is very small with respect to 90 degree, so cos alpha is approximately equals to 1 and sin alpha is approximately equal to alpha. And accordingly, after opening the bracket, we have cos omega Ct into cos omega Mt minus sin omega Ct into sin omega Mt minus alpha sin omega Ct into cos omega Mt. Here the first two terms become the formula of cos omega C plus omega M into T, and in the second term there is sin A cos B, and the formula is 1 upon 2 within bracket sin omega C plus omega M into T plus sin omega C minus omega M into T. And accordingly, output V naught equals to cos omega C plus omega M into T minus alpha upon 2 sin omega C plus omega M into T minus alpha upon 2 sin omega C minus omega M into T. Here the first two terms correspond to upper sideband because there is a positive sign for frequencies, and the second term correspond to lower sideband since there is a negative sign. And in this SSB generator, we retain only upper sideband. So the undesired sideband is lower sideband. And from the question, we have to determine the ratio of undesired sideband amplitude to the desired sideband amplitude. And the amplitude of upper sideband is under root of 1 plus alpha upon 2 square. Because the first term having amplitude of 1 and the second term having amplitude of minus alpha by 2, and the resultant amplitude is under root of 1 plus alpha by 2 square, and the amplitude correspond to lower sideband is simply alpha by 2. Now for the amplitude for upper sideband is under root of 1 plus alpha by 2 square, and after approximated using Pythagoras theorem, we get 1 plus 1 upon 2 into alpha square upon 4, and it is approximately equals to 1 plus alpha square upon 8. Now, according to our question, the ratio, that is undesired sideband amplitude, that is lower sideband, and desired sideband amplitude, that is upper sideband, and it is equals to ratio of alpha upon 2 and 1 plus alpha square upon 8. Now in place of alpha we can write 2 pi upon 180 radian, and calculating we get 0.0175 or 1.75%. Also in terms of decibel we can determine the ratio, and it is equals to 20 log to base 10 into 0.0175, and after calculating we get minus 35 decibel. So in this way we can solve the problem of SSB generator. Here the SSB generator is of phase shift type, and the output is single sideband suppressed carrier. In order to retain lower sideband, we take positive sign, and in order to retain upper sideband, we take negative sign. So accordingly, output V naught is equals to V1 minus V2 when we retain upper sideband, and output V naught equals to V1 plus V2 when we retain lower sideband. So accordingly, we solve this problem.